Hello and welcome back to Calculus 2, section 6.3 on disk method. So we are going to look for the volume of the object. We're going to calculate volume of the object. So let's go and say calculates volume of the object. I'm not going to write 3D object because there are no 2D objects, right? There are 2D drawings. you don't have a triangle walking down the street. So calculates the volume of objects. Now these objects, these objects, there we go. These objects all have to have a very specific quality, and this is that they have to be circular. They have to be round. So at this point in time, I'm going to model this bottle over here, and you will note the circle over here. You will think of all the cylindrical objects. Now look at all of these bottles around. Every single one of them. It doesn't have to be a flat edge over here. All of this, including this part, excluding the nozzle on top, right, is going to be something that we consider. So all of the objects that you can create by rotating a function around an axis. Now, I'm not sure if you are familiar with any of the machining, but there is a machine, it's called the lathe, very good, which you put in a piece of wood or piece of metal, and you bring a knife to it, it cuts into it and creates round objects. Because it spins that wood very fast, as soon as you push the knife next to it, it starts carving the wood or the metal, and then because it spins, it carves equally everywhere, radially, right, everywhere, and you get a round object. So can you get something like this out of that procedure? The answer is yes. You would suspend this object on that lathe like that, right? And when this spins around, you bring a knife from this side, and let's say that this was one long piece of plastic. I mean, that's not how you make this bottle, but let's say this was all solid, and you needed this much. You would just push the knife in, and as the knife cuts in slowly, because this rotates, it will carve this particular shape out of it. Obviously, your furniture is full of those kind of things. If you have those, you know, on stairs, you have those decorative pieces and so on. That's all made that way. So what I'm going to do now is I'm just going to say that, you know, you have some kind of a round object which would have an axis of rotation, and this is the x-axis of rotation, so I will call it x rotation this way. We can also think of the, would you please model the bottle for everyone? Yes, that's it. So just, yeah, that's a cylinder, thank you very much. It would look something like this. We'll ignore the cap, and as it stands on the desk, there is the axis of symmetry here. This is the y-axis, and we will have this y rotation, which we are going to denote this way. So these are the two ways to rotate around x-axis and around y-axis. We will not be rotating around any other lines. We can draw other lines, but we are not going to use any rotation. X and y rotation is fine. I can create most of the, obviously I think, or all of it stuff is, all right, so there we go.
You get that on your clothes,
it's gonna require new clothes. Don't worry about it, Malaysia never closes. Anyway, it's truth. So now, what do we have? We have, we want to construct the object. So what do? Let's say I draw a line. line segment like this. And I say X rotation. What happens as I rotate this around X axis? What do I get as a result? That's very close.
Like a cone?
Cone with a head cut off. I like that. I never heard that before, and I love it. Cone with a head cut off. Yes. So, yes, it's going to be a cone-like object because you will have this line, and then there will be this, and there will be this. So technically, we are having something like this. Now, what can you say over here? You can say we're getting the lamp cover. We're getting the, if you keep it this way, you're getting the, the plastic cup, right? You can do that. So whatever, plastic cup, or the lamp shade, right? You have to understand that this object is solid. It's filled inside, right? The cup is not filled. I mean, yeah, you put something spicy in it, but the thing is that the cup is actually a very thin wall, right, of plastic material, and it's empty until you put some sorrow in it. The lampshade, same thing, right? It's just either plastic or a fabric around, and then it's just empty inside. I need you to know that this is actually all solid block inside. It's all solid material. It's not empty. So, and the reason is, we'll see, we are taking this area here under the curve, and we rotate that area around the axis, and that actually fills everything with the material. How do I create something that it's hollow? Well, I'm going to rotate, and we talked about briefly about the washer method. I'm going to rotate two functions like this, and when I rotate that, that's going to give me this on the other side, and it's going to give me, so now it's going to be empty inside. Yes, will be so we'll upgrade there. For now, I just need you to know that whatever we rotate is solid block of material inside. So can I call this a cup? No, it looks like a cup, but it's just plastic chunk sitting on the, right? We can call it a lampshade, but there is no place to put the light bulb or anything inside. It's just,
How do you get thickness both ends if you were to take the difference?
When you, oh, you mean the bottom of the cup? Well, you would have to rotate something like that. Right? So we'll deal with that. So as you can see, what I'm doing here is I'm taking a function f of x. In this case, it was just a line segment, f of x, and I rotate that around the x-axis, and I'm creating a cup-like object. This is a good thing for you to put a star next and write project, because one of your questions for the project that is due the day of the final exam might be to go and pick up your favorite cup from your favorite coffee or tea place and do your own calculations. That means you are going to measure the amount of liquid that it holds. You are going to measure that cup with ruler or those what is it called? Calipers, thank you very much. With a caliper or the ruler or whatever, depending on which precision you want, measure the dimensions, run calculus to question, and then say, the volume that you're advertising on this cup is much smaller than the actual calculated volume, therefore I don't have to go to school anymore. Right. Let me just see who got the reference. Okay, few of you did. Anyway, so what do we do now mathematically? Well, I have a function f of x, and that f of x is very well defined. Observe that f of x lives between a and a b on the x-axis, and the volume of the shape that it would create is going to be pi integral a to b f of x squared dx. So this is the formula, and I like to write the formula and then explain the formula rather than derive the formula. And here is why. we are going to, well, we all understand, right, so far, that each of the objects that we'll be dealing with in sections 6.3 and 6.4 are going to have circular base. Now, if you paid attention in your Calculus 1 class, you know that every cylindrical object, right, that doesn't end up in spike has a volume of area of the base times the height. Do we all remember that? So every object that is of the, that looks like this, right? So we have this one, we have this one. Well, you can have anything that it's prism like this. It's always going to be volume is equal to area of the base times the height. So area of the base, and this is height. If you have spiky objects like pyramids and cones and so on, there will be a 1/3 of that. So now you know all of the volume formulas, right? As long as you can calculate the area of the base, you will be multiplying that with the height of the object, and you're done. If it's a spiky object, cone or whatever, you are going to multiply that by 1/3, and volume is done. Now, please observe that for rotational objects, which is what we are focusing on, you have your base to be pi r squared area because it's a circle. Every time you rotate, we are not going to have ellipses or anything else. It only can be a circle. No matter which bottle you pick up, it's always a circle. You have the bottles, you have a cup over here. There it is. This is exactly the thing that we had before. Look at that. It fits right here. That's how you get the cup, right? So, always a circle on the bottom. Now, what's happening with these? What's happening with this calculation? Well, if I am to take this object and tip it over on its side, then my base is here, and my height is here. Bueno? See? Okay, good. Now, please observe that the distance from the x-axis to the function f of x is actually your radius r. So your r is actually f of x. Are we all bueno on that? So, does our formula make sense? So, do we all see that r is actually the function? R, radius of the circle, is actually as high up as the function goes. So the function is the radius, and if you look at the formula, it just makes so much damn sense. It's insane. R squared pi. Pi is a constant. You can put it in or out. It doesn't matter, right? Do we see r squared pi? Mm-hmm. Times the height, which is a to b, dx. Right? That's the height of the object. Because a to b, of how long, right? Clearly, this one is shorter than that one. Look. Right? So a to b, if I put them side by side, right? This one, a to b is this much, this one, a to b is that much. So, the height of the object is given by a and b, and the area of the base is given by r squared pi, which is f of x squared pi. Done.
So that's the entire function squared?
That's
F squared.
Yes, entire function squared. So now, your job is to figure out what kind of a function you have. If it's a constant function, you create objects like this with a straight edges, right? So this is, you will literally measure from the center to the outside. Let's say this is 1.5 inches, 3 inch in the diameter, so 1.5 inches on the side. To create this particular object, all I need to do is to draw 1.5 inches straight line. When I rotate that 1.5 inch straight line around axis, I will get 3-inch wide rotational cylinder for that. What's the height, A and B? Well, that's going to be the height from A being at 0 to B at the top, if you don't want to deal with the top. So, the question is, if education was any better than what we have, the only homework you would have from this section is everyone gets a different bottle, one of those, one of these. You go home, and the only homework you have is to tell me what the volume of this is, right? That will be the only homework for this class forever. Now, is there a way for me to do this? Now, I'm just going to use this grid real quick on the board. I will explain what happened. What did I do with my... right there. So now, what do I have? I have x-axis somewhere on the square grid. I place my object, and then I trace my object on it. Ta-da! There we go. And now what do? You rotate that around. So now, if I just say, okay, this is flat, it's going to be flat like here, and then it's going to go like this, from A to B, this function here, y equals, well, f of x equals, let's say 1, and this, what? We want to use exponential, we want to use polynomial, right? Something is going to fit through, you pick 3 points, fit the polynomial through it, I don't care, right? You do one integral for this part, one integral for that part, add them together, and there you go. You have your object. This is how easy it is to deal with engineering once you understand the concepts, right? At that point, you know exactly what the volume of this is because it's computed. You don't have to play with water, with those measuring cups, right? Because they could be wrong. Some students found by working out these things that their measuring cups they have at home are off, right? Especially if you're really OCD, and we have some really awesome people working at the chemistry labs over there, you can go and check it there with the equipment that is certified to measure liquids. Perfect. And my math club did that 5-6 years ago. In members of math club, they went to the chemistry lab and they did a few of these experiments. They did related rates. They did water displacement for Calc3, and they also did these volumes for random objects to find in the Coke can, right? What is the exact volume inside? Yes.
What's a weird function? Like, would you break it up into more basic? So say you like.
If you have a weird function that cannot be integrated, you have to use numerical methods. On day one, I said that not every function can be integrated, which is why eventually we are going to do power series, which will help you integrate technically anything. We did talk, I believe, you and I, about power series and insanity of what they can do.
You would do, say, you come up with a formula for that curve.
Yeah, you can't do everything in one shot, right? Yeah. Because it's a different function. So you have only one function inside the integral. So you do this much, and then you add the next one. Maybe you have more, next one, next one, right? So, I mean, I gotta borrow your bottle now. It's sufficiently annoying. If you look at this thing, right, design of the grip and all of the curves and so on, the function for this is not going to be fun at all, right? The cup over there and these two bottles, they are not the problem, but you have one of these two, right? And coming up with all of these little nukes that they have here, it will be really annoying.
Wouldn't something like
But it's doable.
be easier if you made infinitely small slices?
Well, that's what this is. I'll explain that as well.
Okay.
We're coming up with it. So I hope we are understanding that this formula is just circle, area of the circle times height on steroids. So let's calculate let's calculate the volume of the actual Coke or Sprite can, because we can go online and get the exact measurements of the Coke can or whatever. So we're going to jump into here and say Coke can measurements in North America. Standard can size is 12 US fluid ounces or 355 milliliters. So that's the standard. It is 4.83 inches high. So when I look at the can, it is 4.83 inches high, and diameter at the lid is 260. So diameter, which is actually across like this, is 2.6. Great. That gives me the radius of 1.3, and it gives me the height of the can of 4.83. So now, when I place this, all I need is a single line. Thank you. So all I need is a single line. If I draw a line over here, that line needs to stretch from 0 to 4.83 inches. On x-axis, we are going to rotate on the x-axis, and this height over here is at 1.3, creating this function f of x to be 1.3. It's a constant function because the Coke can is flat. So as I rotate this, I'll use, let's say, blue, it will create the Coke can around, right? It will create a Coke can as I rotate that function. Now, to create the integral for this, we are simply going to say volume of the Coke can is going to be pi times integral 0 to 4.83, and we are taking the function 1.3 squared dx. That's it. You take the function. Now, this function is a constant function, 1.3, so it's very, very easy. We'll take some spicier examples from the book. So now I have this. All I need to do is to integrate this. So I have 1.3 squared. That's going to be 1.69. So 1.69 pi x when I integrate, computed from 0 to 4.83. And then we have 1.69 pi times 4.83 for the total. Let me punch this in the abacus over here. So 1.69 times pi times 4.83 to give me 25.64 inches cubed. Actually, I should go one more decimal place, so 644. You can go one more decimal place because your precision of numbers coming in were 2 decimals. Your calculation, you can go an extra digit. So 25.644 inches cubed. Now you have to convert that to the fluid ounces. You look up conversion between inches cubed and fluid ounces, multiply by the factor, and you better get this 12, the value of 12 in there, because that's what's advertised as a volume. So these problems are fairly simple. You see the function, you just plug that in the integral, square it, and then you do the computation. Don't forget the pi. We need the pi for because the area of the circle is r squared pi, and your function now is your radius. So let me jump to homework assignments. Take a look at one of the examples to give another example. So as you are looking at the homework exercises, we'll take a look at number 17 with the triangle. When you rotate this triangle, you will get a cone. When you rotate the triangle underneath in 18, you're still getting a cone, right? Because there will be a spike at 0, there will be a spike at 1. Now, we are not getting a spike when we rotate number 19, because you see it's cut off at ln4. So this would have a flat edge, right? A circle on top, and we'll have a fat circular bottom, right? And there will be no spikes on that object at all. Move to the other side, rotate this one, rotate this one. See, this is now rotation on y. Obviously, we're going to use a dy integral for that. So let's go and do the one with, let's say the one with e. So let's take a look at problem 19. There are plenty of problems for you to practice. Obviously, the online homework will produce a lot. So problem 19 in the textbook has this exponential function. Whee, there we go. Ends at ln4. So we are looking at 0 to ln4. And the function given is y equals e to the negative x. We are going to rotate on x-axis. It's very important because you are getting completely different shape if you rotate on y. Do you all see that if you rotate on y, you can get like a stand for umbrella or a flag or something, right? You just need to drill a hole over here to stick that in. Do we all see that? Great. So this is what we have for if you do a y. But if you do the x rotation, your shape is something like this. Right? That's what the shape would be for rotation on x. So practice, draw these shapes, see what they come up with. Now, as I mentioned, calculations, we have our a and pi first, and then we have 0 and ln4 as our limits. We have our e to the negative x squared and dx. Exponent of the exponent, we multiply, right? So this is pi integral of e to the negative 2x dx, 0 to ln4. And this is now where Calc 1 kicks in. If it's not a basic integral, it's u sub for the entire chapter 6. If it's not a basic integral, it has to be a u sub. Well, in this case, u equals dx. I mean, if you memorize the formula, go ahead, just write the answer, right? If you memorize the formula, you know that this is e to the negative 2x divided by negative 2, computed from 0 to ln4, right? That's what you have. If you did not memorize the formula, e to the ax over a, you are okay to say u equals negative 2x, du equals negative 2 dx, and then plug in and eventually get that. So you either know the shortcut formula or you are using u sub, whatever. Now we have pi times, plug in ln4, so we have, you know what, I'm going to kick this negative 1/2 outside, so this becomes negative pi over 2 outside, so I don't have to worry about it. I have e to the negative 2 ln4 minus e to the 0. This is negative pi over 2. And now this negative 2 goes in and as the exponent of 4, here in green on the side, e to the negative 2 ln 4 is the same as e to the ln 4 to the negative 2, which is just 1 over 16. Because 4 to the negative 2 is 1 over 4 squared. 4 squared is 16. So 1 over, and then ln and e cancel. So we have 1 over 16 minus 1. That will give me, great, it's giving me a negative number. You don't want negative volume. So we are getting negative 15/16, no coughing, which is 15 pi over 32 as the answer. So that would be the volume that is confined within this. Now, as engineer, why do you want volume? Well, volume is the amount of material it takes, right? You have to order a truck or a train of raw materials to make something, right? Well, you just don't, okay, give me 2 trucks of this stuff. It's expensive, right? As engineer, you have exactly how much material goes. So we order as a company, a factory, or whatever, we order exactly what we need. You don't just go, like when you're painting your living room. Yeah, give me a gallon. Because you know that you will be going to Home Depot at least 2 more times to do anything. Because you don't do calculations. You just say, Business doesn't work that way. You're either making money for the company or out you go. So you have to compute these things exactly, right? You are making a product, whatever that product is, you have to have exact volume so we know how much material we have to, raw materials have to be ordered for that. Great. By the way, does anyone know about a handheld object of infinite volume? See, I have a finite volume. I don't think that any one of you can lift me. And I have a finite volume. How about holding an object of infinite volume in your hand? Possible or not possible? If you know it, go ahead, say it.
It's that vase-looking structure, right?
Vase-looking structure, yes, which is called, does anyone know?
Oh, a Klein bottle?
Klein bottle, very good.
I was going to say a projected plane, but that's not three-dimensional.
Klein bottle, yes.
Yeah. Klein bottle inspection, but it can't really, it's non-oriented.
Oh, there you go. Klein bottle, images. See, it actually stores the... I know it folds on itself. Yes, welcome to topology. But it's not a rotational object. It doesn't really fit the lecture, but it's cool as hell. So
That looks like a windy camper.
yeah, people print this on the 3D printer. So yeah, go ahead. And here's one held by in the hand. Here's the one holding brandy. Obviously, people say it's tea. It's not tea. Tea.
How does it have infinite volume?
Because it's inside, it's outside.
Oh.
Yeah.
So it takes all of the space in the universe.
Yeah, if you actually make a glass one, it's not a real Klein bottle.
Well, actually, it is.
Do you get stuff
Well,
out?
in,
Oh.
Yeah, you get stuff in and you get stuff out.
Oh.
There is a hole on this hole.
yeah.
See this hole in the bottom?
yeah, all
The hole
things
in the
on
bottom
outside
goes
are also
all
things
the
on
way
inside.
up, and then it fills the space here, but it's a hole. So this inside space is leaking through the hole outside. So inside is the outside at the same time. There is a similar object in 2D. What is the object with the infinite surface area? Mobius strip. Very good. You take a long string, a strip, and you just make one twist and connect it. Has infinite area. Because you go around, you end up on the other side of the tape. So anytime you make a full circle, you end up on the other side of the tape. It has infinite volume. There are other mathematical concepts that you can build on top of that later on. No, you just say infinite, it's easy. V equals infinity, done, no integrals. I'm sorry?
What's the proof?
The inside is outside. There you go. Done.
Once you
It's very
fill that
simple.
up, that's it, right?
No, because it keeps going.
Yeah. People do all kinds of funny stuff with this. I saw someone actually knit a hat. Here is the 3D print. We have our 3D print master over here.
For you.
At one point, I did see someone. Oh, there it is. What is this? Oh, that's a zippable bottle. Oh, there they are. There you go. That's what I was talking about. See that? Yeah. Someone knit the Klein bottle
Because it keeps going.
into a hat.
Does that keep you infinitely warm? Your head infinitely
No,
warm?
it just makes you infinitely smarter
Oh, okay.
and goofier when you show up. Because you go to the party and say, wow, that's a cool hat. Bring up the chair. Let me explain everything about this. At which point they leave the party and there's more cake for you.
I like the beer glass.
The beer, yeah. It's tricky to drink out of it, but it works. Okay, cool. So that's that part. So for our purposes here for the lecture, we can also have a rotation on the y-axis, in which case you are going to have the y integral with c and d on the limits. So rotation on y, we'll have. I did push the button. Well, looks like in this room I have to push it twice.
Yeah, I guess you.
Or mentally threatened. All right. The panel, not you. Relax.
Of course.
It's too early in the semester. So we have now f of y squared dy. So function needs to be in terms of y. Our limits are c and d, which are y. Rotation is on y. So it's now y across the board. Our accompanying image over here would be something like this, with a rotation on y-axis to create this stand-up cylinder, right? And this one over here is f of y. X equals f of y. Immediately, problem to solve that. Uh, 22 is an excellent example. So it says y equals 0, y equals ln x, y equals 2, x equals 0, and y rotation. The first order of business is to graph all of these functions and see what shape it takes. So the one function that I can graph is ln x. That goes through 1. I also have y equals 0. Well, that's x-axis. Y equals 0. I have y equal to 2. Well, that's going to be here. And x equals 0. That's this puppy here. Okay. We are able to find a shape. And I will shade that shape. We are rotating around y-axis. So I don't even know what this is. I just know it's really sharp. All right. It looks like this. It goes in, has where this edge, look at that. This edge around this object is incredibly sharp, right? Because of this part here. So that's what the object would look like. We can put our y-axis rotation right there as the result of rotation. Now, to find our volume, we simply start with pi. Observe our delta y representative rectangle. Bottom is 0, top is 2. And now I need this function here. I need this as x of the function of y. So that means that I have to flip this. Solve it for x. So how would you fish out x out of ln? E both sides, very good. So we'll have y equals ln x, and then we e both sides. So we are getting that x, oops, I wanted to do blue. So we have that x is equal to e to the y. So this is e to the y squared dy. Everything has to be in terms of y if you are rotating around y. Everything has to be in terms of x if you're rotating around x. So we have pi integral 0 to 2 of e to the 2y dy. Integration and everything works the same. So this is pi e to the 2y divided by 2, computed from 0 to 2. This is pi over 2 e to the 4 minus e to the 0, which is pi over 2 e to the 4 minus 1. That's exact. Now you can go and can punch this in an abacus, come up with decimals if you're engineer. For lazy mathematicians, this is exact answer, we just walk away. It is justified. Our answer is better because it's exact. Your answer is better because you're an engineer and you're actually getting paid. So, for that one extra step of coming up with a decimal at the end. Right?
Don't do that speech.
Oh, you're a math major?
Yeah.
Oh, poor thing. This is what you got to look forward to.
Oh, boy.
Fat and no hair.
At least I get to wear a turtle. At least I get to wear a turtle.
All right, great. So that was the sideways. The next question is, what if the object is hollow? If the object has a hole, right? The holy object. What do we do? Well, in this case, we use the general form of the disk method, which is called the washer method, and this is where the difference, something similar to your area between two curves, kicks in. Say we are producing pipe in my factory, or plastic, right? We are making PVC pipe. I need to know how much raw material I need to create a PVC pipe. Now, PVC pipe is hollow inside for water or whatever, blood to go through. Gasoline, no, you don't put gasoline to plastic pipes. Yeah, exactly, depends on the material. That's why we need chemical engineering and others. As a kid, I tinkered with stuff, and I put thinner in a plastic cup and just melted through it, and then ruined the table as well. As you can see, I lived, but it was close. It was close. That was one of the close calls in life. So, chemical engineering apparently very important when you're a kid. I had no clue. Also helps when your parents have shorter hands, but mine didn't. I became chemist very quickly. All right. So what do we do now? Now we have a rotation of two functions, and we are creating objects that will have hollow inside. To explain this, let's go with something that it's simple. Say we have parabola together with a linear line. The object we're going to get from rotating this is garbage. But, you know, mathematically to explain the concept, it's awesome. So the top function, here we go with our top and bottom function, and now you remember the story on which one is on top, which one is on the bottom. Just compute the y values at the same x. If you are not able to do the graph and look at it. We have a top function and the bottom function, and we use the same reasoning as for the area between two curves. We calculate all of the volume, then we calculate what we don't need, and we subtract. So that would lead into what we call the washer method. And 1-800 phone call. So I have to take this. I love it. Hello? I'm sorry. No. He passed away last week. Yeah, me too.
So good.
Anyway, I love 1-800 numbers. Come on. Okay, so washer method. I'll explain why they call disk and washer method. It's going to be exactly what you guys told me earlier. But now let's just write the formula. So volume is equal to pi a to b. We have f squared of x minus g squared of x, right? So you square each function and then you subtract them, dx. That's the x rotation. And another one for y rotation, c to d, of f squared of y minus g squared of y, dy, y squared. Perfect. Now please note, as the areas as well, this is the general method. Because all you need to do is to have your g equals 0 to go to the previous method, right? So this is the most general case, right? This is the general case that you study. And if your g function is the flat, the axis, x or y axis, then you have your disk method, right? If it's a function, then we call it washer. So note that when you create this object, over here, the object would be something like, I can do red. So the object would be something like this. This is what the object would look like from outside. It's going to be round. But on the inside, there would be a conical, hollow space inside, because this over here is empty. Remember that when this starts rotating, this area will swipe towards us, right? And then back onto the page, and then past the page on the other side, coming back into its original position. So we are going to see full material over here, plastic, wood, whatever it is. But when you look, ooh, look at that. That's an eye. When you look from this end, you will have a hollow part in here. There will be empty part. What?
3D molecule. I feel like
yes.
I'm chemistry right now.
You should, because this is base for everything.
Here we go.
Here we go, right? Yeah.
If it weren't for math, people would not survive.
No, we would. It would just be much less of us.
Yeah.
Because we were still running from tigers and things.
Because they have to make the sharpest knives. They have to calculate how to make them.
Exactly. You have an idea. All right. An example for washer method, number 24, for you to enjoy. I will draw the picture, we have this, and we have this. The one on the top is the fourth root of x. The one on the bottom is x. And that's all you get. Rotation on x. Rotation on x-axis. So what is the volume of this object when you rotate this area around x-axis? What is the volume that you would get?
Is that the fourth root of x?
What happened?
Yes.
Is that the fourth root of x?
Yes.
Fourth root of x, yes.
What was the question?
Find volume.
Okay. That's all they give you? They don't give you what the B is?
You have to equal the two. Solve.
Oh.
Mm-hmm. There's a way to fix it. Take the glasses off, and then put them back. You'll remember next time. All right, so here is the calculation. We equal two functions to calculate limits. Please remember that you are not allowed to cancel x's on left and right, divide by x both sides, because x could be 0, and it is, in which case you would lose a solution, right? So the way to solve equations is to subtract everything to the same side, or add to the same side, and then factor. That will allow this 0 to survive. From here, if you cancel x on each side, all you're going to get is 1 equals x cubed, and at that point you just killed your 0. You killed your a. You have no way of retrieving it back. So the trick is to subtract x to the other side and then do the factoring, which would give you both solutions, x equals 0 and x equals 1. I know we did this with the trig function on day 1, where I told you you are not allowed to divide by sine and cosine and tangent because they could be 0, right? Sine of 0 is 0, sine of pi is 0. So you can't divide by sine x because x could take values of 0 and pi and 2 pi, and in that case you are dividing by 0, which is not good. So because x can take a value of 0, you are not allowed to divide by x in this particular equation. So you have to subtract it, factor it, and then come up with a... Now we also see on the graph that fourth root of x is on top. So now to set up our integral, we have top squared minus bottom squared. So we just use algebra to plow through these calculations, and the answer is pi over 3 at the end, if all of this went well. And now the last bit for a minute would be to tell you why is this called the disk method, washer method, and so on. So as we are considering a shape that is, let's say, a cup that might be there on your project or whatever else, when you consider its construction, which is a single line, which is the function f of x in this case, and then rotation around x, you can draw a representative rectangle dx, which would stretch from A to B, which are your limits of integration. So everything you learned before still holds. Now, this one representative rectangle is infinitely thin slice, which means that as you take your cup and you slice over here, you will get that infinitely thin disk. Infinitely thin disk that has no holes, nothing, is just solid circle, right? Infinitely thin. And as you stack infinitely many of those, one next to the other, so that they follow the diameter, the radius diameter of the cup, you would be able to stack them all up and create the cup. And your textbook has a very good graphic for that, to understand what is exactly which way they're stacked together. Let me just get there very quick.
So it's just a Riemann sum on a solid object.
It's a Riemann sum, and instead of adding rectangles, you are adding. So it's a perfect. Here is the perfect. It is a Riemann sum, and as you can see, they stack together. So this is a very rough with a very wide discs. The more discs you put in, the smaller the delta x is, very refined. And this is infinitely many. Perfectly follows the line. Maybe we can even find a better one. Let me see if they have anything else. Maybe here. They do just show a disc in the book, and this one has a hole. So why is it called a washer? If you ever did anything with screws and screwdrivers, and you should because you're sitting in this class, you know what a washer is. At least maybe you put an IKEA piece of furniture together. They have little washers, right? It's a little metal ring, right, that it's flat and has a hole inside for the screw to go through. And it's just there as a spacer and to hold the screw stronger like this. So you don't dig into the wood and so on. That's the washer, right? It has a hole inside, and then you just stack into it. They look like CDs. I don't know if you don't know what those are. CDs, and they used to carry movies, and CDs were for music. I don't know. They used to be around. It's no longer the case. But think of the stack of those with a hole inside. That would be the lecture.
My dad used to have a
Bye.